Hello students, from today we will be resuming our class. So first thing is solving the Einstein equation. So we will start with solving the Einstein equation for a spherically symmetric metric. What do we mean by spherically symmetric metric? Is that this VR, this potential is independent of theta. Okay, so and also we will be assuming that the equation of motion is symmetric under time reversal. That is, if t goes to minus t, this equation of motion doesn't change. Okay, these are very general properties which has been seen to most problems have been seen to have from classical mechanics, so it will be not be very different. So we will be also writing the general metric in a spherical coordinates. Why? Because most of the astrophysical bodies are spherical. Okay, so a spherical coordinate system will be easier to solve. So in a spherical coordinate system, the metric will be of this form: ds square. All the terms will be there. Okay, so this gtt which comes with dt square, tr which comes with dtr, t and r, and there are these diagonal terms rr, theta theta, and phi phi, and along with this the off diagonal, all the off diagonal terms are there, and this is a symmetric matrix, so this 2 comes for the diagonal terms. So this is a very general metric, but we are assuming some speciality about space and time, this will be reduced. So we are assuming time reversal symmetry, that means ds square for t is equal to d dash square for minus t, which means that this rt and tr and all theta will go to 0. Also, the metric g mu nu will be independent of time. This is not a function of time, so anything is not a function of time. As the metric is a spherical symmetric, so for a given r and t, the metric should be a metric in a 2 sphere. Okay, so it should reduce to, for a given r and t, it will reduce to d square to be r square d theta square and r square sin square theta d phi square. So we have done this. So let us next see what the things are there. Also, it is symmetric in theta and phi, so there will be no change in theta as theta goes to minus theta, and there will be also be no change in phi as phi goes to minus phi. So using all these symmetries, what we have is the big metric reduces to a very smaller one, which is given by ds square equal to only this, the diagonal terms, and the diagonal along with this, the d theta and d phi square will have this components. So let us choose this diagonal terms for t and r to be fr and hr, because as we are assuming it to be a function of r only, so there is no function of theta and r phi t, so this is a very good choice. Also, we will be looking into vacuum solutions. What does vacuum solution means? That means we will assume that t mu nu equal to 0. So it doesn't mean that there is no mass or energy momentum. It only means that there is some mass, a massive body, but we are not looking into inside of the massive body, the space-time inside of the massive body, but outside it. So outside it, it will be due to the massive body, the space-time will be curved. However, this nature of the curvature will be given by the metric. So this is a very general choice. This is the easiest problem to solve. So let us start with that. If we choose t mu nu to be 0 from the Einstein equation, what we also know is that the left hand side will also be 0. That means g mu nu equal to 0. If I write g mu nu, so that means r mu nu minus half of g mu nu r is also equal to 0. So multiplying it both sides by g mu nu, this is up g mu nu. Okay, so what we have is, we have a very, if you do that, if you compress it, this is for the dimension of that, this compression. So we have r minus 2r equal to 0, that means r equal to 0, and that means all the Ricci tensors r mu nu are 0. That means all the Ricci tensor components should vanish. Okay, so we can write this in another form, in the form we know, rho mu nu rho nu equal to 0. Okay, so let us see what happens. Now also we have g mu nu equal to this is the diagonal form, and also we can, because this is the diagonal form, the inverse of metric is thus the is the inverse of this metric components. Okay, and we have all the things we need. Hello students, let us start from where we have stopped in this from this video. So now is to solve this Einstein equation. First we need to calculate the this Ricci tensor. Okay, so Ricci tensor can be calculated. So let's do this one by one. First let us calculate this RTT. So we know that RTT can be calculated in this form RT. It also has theta of the form and the phi of the form. Because we are doing this because we know what is the form, how to write this Ricci tensor R rho sigma mu. Okay, in this case rho and mu are same for us, so it will help us. So this, you must remember this form. This Ricci tensor has the form of which involves this derivative, partial derivative, along with the Christopher symbols. Okay, so this is the form. I think you all remember. Okay, therefore let us start with that. If I use this form for each of this term, let us see what are the terms that remains to be calculated to calculate RTT. Okay, so first we have gamma, means this was gamma R TTR, also gamma R lambda, gamma lambda TT, where lambda can be anything from T R theta phi, anything you can put it there and calculate. Also it also has gamma R T lambda and multiplied by gamma lambda RT. It has also gamma theta theta TT comma theta plus gamma theta lambda gamma lambda TT minus of gamma theta T lambda gamma lambda theta T and gamma phi lambda and gamma lambda TT, and also this gamma phi T lambda gamma lambda phi T. You should all check that this is only, these are the only, how many terms, let me see, 1 2 3 4 5 6 7 8, only this 8 terms remains. You can, there will be many terms more if if you choose lambda, but you will see that for only few lambdas this will only contribute. Okay, now this you can calculate this because you know that how this Christopher symbol varies with the metric, because this we have the metric we have, and if I know this, then I can easily calculate all this Christopher symbols, and putting this back in the Ricci tensor, I can calculate my desired thing. Okay, so if I put this all these things value, we will see that this gamma t tt will be 0. Only the non-vanishing components of t are gamma t tr, which is equal to gamma trt, because this is a symmetric metric, which is equal to f dash by twice of f. Next, for calculating r or anything, so this is very general. Also, we will need gamma rtt. I am only writing the non-vanishing term from now on, which will be minus f dash of twice a by twice h. Gamma r theta will be minus r of h. Gamma r will be minus will be h dash by twice of h, and gamma r phi will be minus of r sine theta by h. So students, please check that these are only the non-vanishing terms. This will be a big calculation, but this is a bit tedious, but I think you can easily do that. So you know the mathematics to do that. I think you remember before our class stop. So next, again for theta, we only have these three components, gamma theta r theta and gamma theta theta r, which is both are same and they are equal to 1 by r, and gamma theta phi equal to minus sine theta cos theta. Also we have gamma phi r phi, which is equal to gamma phi r equal to 1 by r, same as the above, and gamma phi theta phi which is equal to gamma phi of theta equal to cot theta. So these are only the non-vanishing components we will be needing. So now if I substitute this in the Ricci tensor equation, we will first, if I calculate RTT, so we will be having this equation minus 1 over 2I h f double dash means double derivative minus of f dash h dash by twice h minus f dash square by twice f plus twice f dash by r, and which is equal to 0 because all the components will vanish as we argued previously. Again r of rr will be minus 1 of twice f double dash minus f dash square by twice f minus f dash h dash by twice h minus of 2 f of h dash by rh, and which is also equal to 0. We need one more equation r theta theta, which is equal to 1 minus r by h whole dash minus r by r over h square f whole multiplied by hf whole dash equal to 0. There will be also r phi phi term, but we will not needing those terms. So these three equations are enough to calculate the Einstein equation. Let us denote these equations r tt by 1, rr by 2, and r theta theta by 3. First, what we do is we substitute, subtract equation 2 from equation 1, which will give us this simple equations twice of f h dash by rh plus of twice f dash by r equal to 0, which is very easy to solve and which will give as f of h of whole dash equal to 0, which means that if I do the derivative, integrate it, then I will say that we will have is f of h equal to c1, some constant. So now let us try to see what this c1 is. Let us look into the metric very far away from the source. So this dr square, which is some gtt dt square, at r tending to infinity. What happens at r tending to infinity? That means we are very far away from the source. The space-time will be very similar to that of a flat metric because very far away, right? The effect of gr will be almost negligible. Okay, and we will be reducing to a special relativity. The metric will be similar to that. If I do that, therefore I know that metric d r square will be minus of dt square plus dr square plus r square d theta square, and plus yeah, r square d theta square plus r square sin square theta d phi square. Okay, this is where will be that of a flat metric in curved space, in in spherical coordinate. Okay, so which means that our f of r will be minus, f of r at infinity will be minus 1 and h of r at infinity will be 1. That means if I put back in this equation, which will give us c1 equal to minus 1, that gives me the relation that h equal to minus of 1 over f. Okay, this is the equation which will let us keep. This is the important equation. Let us keep it and mark it as equation 4. Okay, so now we have equation. Let us combine equation 3 and 4, and this will give that a single equation 1 minus r by h whole dash minus r of over h square f by h of f whole prime equal to 0, which can be easily solved because this is, we know, is a constant one. This will go to 0. So this, therefore we have r by h of whole prime equal to 1. We can solve this, integrate again, which gives us h r by over h is equal to r plus c2. Okay, so which we have, if I can write it, is 1 over h equal to 1 plus c2 by r equal to minus of fr from our previous equation 4. So let us choose this c2 to be rs because this is only writing in some form, but we will know what rs is and why we have written in terms of rs as we proceed forward. So let us write this. So we can again write minus of f of r equal to 1 over h of r equal to 1 minus rs by r. Okay, so next, if I once we have done this, let us see what our metric looks like. And the metric looks like is d square is minus of 1 minus rs by r d square plus 1 minus rs by r to the power minus 1 dr square plus r square d theta square plus r square sin square theta d phi square. If you have earlier have seen this Schwarzschild metric, you will realize that we are getting something very close to that. Okay, only we need now is to find rs. Okay, so the thing only remains to find the Einstein equation. So hello students, let us resume our class. We are not still finished because you remember we will be now starting to see, now we'll be doing that what rs is, trying to fix rs. Okay, it has the dimension of radius or space or length. Okay, so let us try to fix that. Okay, so remember that we can also write now all these components that we have written in terms of f and g in terms of rs. Okay, so these are the two examples, two of that. This gamma tt rt equal to rs by over 2r, 1 by r minus rs, and gamma ttt equal to rs over 2 by r minus rs. Okay, so let us do this, and from our known problem of central force, we know that in a central force problem the motion is planar. So for planar thing, we will be choosing a planar coordinate in this thing. So to choose a planar coordinate, what we do is let us put theta equal to pi by 2, which implies that the theta equal to 0. So we are in a plane. Okay, we can also write the action in terms of the Lagrangian. Okay, so we know what is the Lagrangian is. Okay, so this is the kinetic terms having r and phi part. Okay, this is, remember that this is a Newtonian calculations. We are not going into the gr, so there is no t here, means t doesn't appear, only appear here. T doesn't appear in the metric, and there is no theta because we are choosing a plane. So this is the kinetic part, and this is the potential part, and we know what is the potential part. What is the potential? Vn is equal to minus gm by r from our known knowledge of Newtonian physics. So let us now write the equation of motion from the, we know the Lagrangian, right? We can write the equation of motion. Let us write the equation of motion for phi. So which is given by d by dt of del L by del phi dot minus del L by del phi equal to 0. And I think each of you can solve this with this given Lagrangian to find out that we will having this our known relation r squared d phi by dt equal to L by m. L is the angular momentum. Okay, so it also says that the angular momentum should be conserved. Okay, and some quantity is conserved, which is the angular momentum, which is denoted by L. Okay, we can also write the equation of motion for r, which is gives d by dt of del L by del r dot minus del L by del r equal to 0, from which we can easily see that write in terms of total derivative d square r by dt square equal to minus del L by del r of this Newtonian potential plus a extra term, which is L square by m square r cube. Okay, we can write this in terms of a effective potential. Okay, del by del r of Vn effective, where what is Vn effective? Vn effective is the effective potential, which is the potential which already we have seen, plus this term L square by 2 m square r square. Okay, so if I expand it, this will be minus gm by r plus L square by 2 m square r square. So this is the total effective potential we have, and the equation of motion for r can be written in terms of this equations. Okay, now this is all about Newtonian physics. So let us go to gr. In gr, what we have is the geodesic equation. Okay, so let us write this geodesic equation. You all know the famous geodesic equation, we have derived it earlier. Okay, so our affine parameter here is, say, time, or the proper time, because this is a good affine parameter. for a massive body. Okay, so let us now do this geodesic equation for phi. Okay, so if I write the geodesic equation, expand this, so you can easily see that this is d square phi by d tau square plus twice gamma phi r phi dr by d tau d phi by d tau plus 2 gamma phi theta of phi d theta by d tau and d phi by d tau equal to 0. Okay, so if I because we know all this gamma or the Christopher symbols, we can put it here, replace it here, and we will have a equation of motion for phi, which gives us, which is very similar to that of the equation of motion that we got for phi for Newtonian case. Only here the t is replaced by tau. So therefore we should once for going from the gr to the Newtonian limit for the phi case, we should identify that here this normal time should be replaced by proper time. Okay, so this is the first identification that we make. Let us go to the second identification. What is the second identification? Let us write for mu equal to r. Again, writing the geodesic equation, expanding it, d square r by d tau square, we will have only this term with gamma r tt, gamma r r r, gamma r theta theta, and gamma r phi phi. Okay, so now we again we know this, what are this from our solution of the metric. So we can calculate this, and this becomes of this form: d square r by d tau square rs by twice r cube r minus rs dt by d tau square minus rs by over 2r r minus rs dr by d tau into r minus rs l square by m square to the 4 equal to 0. So now we are stuck. We don't know how to solve this because there are many things, but we are saved because if we remember that what is the definition of proper time? Proper time is nothing but the negative of the line element d square. Okay, and d square we know for this, for our chosen this metric is of this form. Okay, so let us divide both sides, this d tau square and this with d tau square, and see what happens. So this becomes 1, and this becomes dt by d tau, this becomes dr by d tau, and this uh, will be r square l square by m square to the power 4. Okay, so how this comes, just check. This is very straightforward. You don't have to do much, but you just want to do it yourself. Okay, so I can write dt by d tau in terms of the other dr by d tau and the constant terms. If I do this, I will have this equation. Let us write this as equation 2, and our this equation we need to solve is equation 1. And if I replace dt by d tau from 2 in equation 1, what we have is, we'll have this big equation. But don't get afraid from with this big equation, because most of it will cancel. Okay, we have d square out by d tau square. Okay, and both dr and d tau square, so you will see that many of things will be cancelled. Do it yourself. Okay, so if I do this calculation, you will see that only this 4 terms remains: d square r by d tau square plus rs by twice r square plus l square by twice m square r to the power 4 minus l square by m square cube plus rs by l square by m square to the 4 equal to 0. If I take d square r by d tau square on the left hand side and all the other things in the right hand side, we can now write this in terms of a partial derivative, and this a single term in terms of a single, not single, let me say 2 terms, and let us call this as just effective potential. That this is similar to that of effective potential that we have defined it for the Newtonian case. Only difference is that there are some more extra terms. What are the extra terms will be coming later. Okay, so what is this G effective? G effective is R minus Rs by twice R plus L square by twice M square R square 1 minus Rs by R. Remember that, recall that what is the effective potential for the Newtonian case? It is similar to this, but here we have Gm by R, and here we have, instead of this extra term, we have only the single term. So if I want to make GR approximation from the Newtonian term, what are the things that we need to approximate or need to identify? That t goes to tau, that means simple time goes to proper time. This Rs which we have trying to identify is equal to of twice Gm. Okay, so Rs should be equal to twice Gm, and this term Rs by R should be very less than 1, so that this will be very small and this term dominates, and we have this only the single term. So if once we have identified Rs, we can put it back in our metric which we want to solve, and finally we have this the metric for this spherically symmetric space-time, which is a vacuum, and it is given by this line element is minus 1 minus 2 gm by r dt square plus 1 minus 2 gm by r to the power of minus 1 dr square dt square plus r square sin square theta d phi square. This is a very famous metric. This was the first solution of the Einstein equation, which was done by Schwarzschild, and this is known as Schwarzschild metric. This metric is true for any space-time which is spherically symmetric, which is stationary, if the metric is stationary, static, and we are looking for a vacuum solution. So this is the famous Schwarzschild metric, and we have finally arrived there. Thanks.